Today we explore the max flow min cut theorem, one of the cleanest ideas in algorithms. It says that the most you can send through a network is exactly equal to the capacity of the cheapest bottleneck that separates the source from the sink. A flow network is a directed graph. One vertex is the source, called S, and another is the sink, called T. Every directed edge has a capacity, the largest amount of stuff that edge can carry. The stuff could be water, data packets, jobs, or even matching choices. A flow assigns a number to each edge. There are two rules. First, capacity. No edge can carry more than its capacity. Second, conservation. At every internal vertex, whatever flows in must also flow out. Only the source creates flow, and only the sink absorbs it. Now imagine cutting the network into two sides, with S on the left side and T on the right side. Any flow from S to T has to cross from the S side to the T side somewhere. So the total capacity of those crossing edges is an upper bound on the flow. The max flow min cut theorem says that this upper bound can be made perfectly tight. The largest possible flow value equals the smallest possible capacity of an S to T cut. So a routing problem and a bottleneck problem, which look different, have the same numerical answer. Let us see the theorem happen in a concrete network. Each edge label has the form flow over capacity. We start with zero flow everywhere. Then we repeatedly look for a path from S to T with spare capacity and push as much as that path allows. The first path is S to A to C to T. Along that path, the capacities are 16, 12, and 20, so the bottleneck is 12. We push 12 units. The total flow is now 12, and edge A to C is full. Next, use the path S to B to D to T. Its capacities still available are 13, 14, and 4. The limiting edge is D to T, with capacity 4, so we push 4 more units. The total flow rises to 16. A third useful path is S to B to D to C to T after the previous pushes. The leftover capacity along that route is 9, 10, 7, and 8. The bottleneck is 7. We add 7 more units, bringing the total flow to 23. How do we know we are done? We look at the residual graph. A residual edge records how much more flow could go forward and also how much flow could be undone backward. If there is still a residual path from S to T, we can augment again. Here, the remaining possibilities get blocked before reaching T. Now take every vertex reachable from S in the residual graph. In this example, the reachable side is S, A, B, and D. The other side is C and T. The crossing edges are to C, D to C, and D to T. Their capacities are 12, 7, and 4, totaling 23. This gives the proof idea. Every cut is an upper bound on every flow. When no residual path remains, the vertices reachable from S form a special cut. All forward edges across that cut are saturated, and all backward flow across it is 0. Therefore, the current flow value equals that cut capacity. Algorithmically, this is why augmenting path methods are so powerful. They do not just produce a large flow. When they stop, they also produce a certificate, a cut of the same value. That certificate proves no larger flow can exist. The theorem appears far beyond pipe networks. It supports bipartite matching, scheduling, project selection, network reliability, and image segmentation. In each case, max flow searches for what can be routed, while min cut explains the bottleneck that prevents anything better. So the memorable slogan is this: maximum flow equals minimum cut. Flow tells us how much can pass. A cut tells us why no more can pass. The residual graph is the bridge that turns an algorithm into a proof.